interface memory devices and input output devices through the system bus to build a complete system. So, microprocessor independently cannot be used to build a complete system. So, you have to interface memory and IO devices. Second important characteristic is, because of this feature that memory and IO devices are not part of the CPU, it has provided you flexibility and versatility. How? The versatility and flexibility has come because the memory and input output devices are external to the CPU. So, you can interface required size or amount of RAM, ROM and different types of input output devices. So, it has provided you the flexibility. You can build small as well as big system using microprocessors. And also it has given you another characteristics, it is general purpose. By general purpose, I mean the microprocessor based systems are not configured for a particular or specific application, and as a consequence the application software is not ROM based. For example, you have your personal computer. At a particular instant of time, you will be using it for word processing. Next time you will be, next moment you will be using it for spreadsheet applications. Next time you will be using it for sending email. So, the software is usually stored in secondary memory. And as and when a particular application is required, you are transferring that part of software, say word processor or spreadsheet software or DBMS, from the secondary memory to the RAM. So, as a result, you are transferring the software to the RAM and then using it. And this has also made another important feature, that the instruction set is designed such that one can transfer program and data between CPU and memory. Rather, by memory I mean RAM. So, from the, that is external to the chip. So, from the external device to the CPU, your instruction set is heard. There is good repertoire of instructions, with the help of which you can transfer your instructions one after the other by using a variety of addressing modes to the CPU and can execute them. And as a consequence, you can build very powerful systems, and that is why the CPU or the microprocessors available in the form of CPU are gradually becoming more and more powerful. For example, in the early years, the microprocessors were simple 4-bit, then came 8-bit. Nowadays, you get microprocessors with the capability of mainframe computers. So, what I am trying to tell, that microprocessors are used for building general purpose versatile system, and it is designed that way. So, CPU is getting more and more powerful, but as you know, the VLSI technology is advancing at a rapid rate, and it has made possible to put all the different subsystems, CPU, memory, IO ports timer counter, and so on a single chip. This has created microcontroller. So microcontroller can be considered as a true computer on a chip. You may be asking, what is the advantage of that? Whenever you have a true computer on a chip, there are many applications where you don't require very powerful CPU. You require very limited amount of or limited size of RAM, limited size of ROM, and very few input output ports. So in such applications, and this type of applications are increasing at a rapid rate. We shall see the different types of applications. In such applications, it is important that the system is realized with minimum number of devices or with minimum chip count. System is small and consumes lower power, occupies very small space, and it can be easily designed. So microcontrollers have come up with this objective. So it can function as a complete system without any external component. However, you have to provide flexibility. Flexibility is also desired so that you can use the microcontroller for a variety of applications. And and incorporating this flexibility, they are designed particularly for embedded application. What do you mean by embedded applications? By embedded application, I mean the system is designed for a particular or single application. So it is not necessary to have all the application softwares in the secondary storage. You have one and only one software, application software. So the application software is ROM based. This is a very important characteristic. And not only that, the ROM is usually part of the microcontroller. It is within the chip. So the instruction set of microcontroller is designed in such a way that very efficiently you can transfer instructions stored in ROM to the CPU. Of course, it is within the chip, and that can be done very easily. So as we have seen, the microcontrollers are designed for embedded applications. Let us have a look at the list of embedded applications, what it can do. It can be used for implementing variety of household items, starting from simple toys, cameras, video recorders, CD players, TVs, microwave ovens, washing machines, vacuum cleaners, garage door opener, home security systems. This list is obviously incomplete. There are numerous applications where microcontrollers can be used. Moreover, it can be used in implementing popular office equipment like fax machines, printers, plotters, modems, smart cards, and also to realize many communication equipment like cordless phone, answering machines, pagers, cell phones, etc., etc. So you see that embedded app, in case of when the microcontrollers are used in implementing embedded applications, it is not visible that there is a computer, but it is implementing in specific applications. The microcontrollers are also used in automobile industry to a great extent for ignition control, so that the pollution or that emission that comes out from the car uh, produces less pollution, or when accident occurs, it protects it. So, these are the various applications for which the microcontrollers are designed. Let us look at the key features of these microcontrollers. What are the very important features of microcontrollers? First and foremost is that oscillator on it must have on chip oscillator. As you know, in case of microprocessors, the oscillator may be part of the chip, may be outside the chip. So, it is not mandatory that the oscillator should be part of the chip. There the oscillator can be designed externally, and then there is a clock input to which the clock can be applied. But in case of microcontrollers, it is essential that the oscillator is on chip. As I have shown in this simple diagram, as you can see here, the oscillator is on chip. It has to be inside the chip. Of course, you will require few external components like a crystal and maybe two capacitors, so that the oscillator it oscillates at the fundamental frequency, not in at harmonic frequencies. And second important characteristics, it must have on chip RAM of limited size. Obviously, it must have on chip ROM, obviously of limited size, and this size is decided in such a way that it satisfies the requirement of most of the applications, majority of the applications. Then it must have on chip IO ports, so that we don't require external IO port chips like 8255 for interfacing different types of input output devices. The IO port should be built in, and in many situations the serial port is also built in. And as we have seen for embedded applications, timer counter plays a very important role. So it is important that the timer counter is on chip. And so these are the key basic features, and as you can see here, you have got the CPU, not only the CPU, the oscillator, the ROM, RAM, a number of input output ports, serial port, timer counters, interrupt control circuitry, then the bus control circuitry. Why bus control is required? You may be asking, you have provided everything on chip. Why do you require bus control circuitry? It is necessary to provide flexibility, so that if the on-chip ROM and on-chip RAM does not satisfy the requirement, in such cases you can interface external RAM and ROM. So it is designed with the option that external ROM and RAM can be interfaced. So this is the generic block diagram of a microcontroller. And apart from these basic features, I shall highlight some very important features which are necessary to implement microcontroller based systems. What are the important features? Yeah, one important feature is a large set of special purpose registers. We have seen in case of 8085 or any other general purpose microprocessor, you have got a set of special purpose registers like accumulator, program counter, stack pointers, base registers, index registers and so on. These are the special purpose registers. But in case of microcontrollers, you will require additional special purpose registers. For what purpose? The main reason for having a large number of special purpose registers is these, you have seen that your IO ports are on chip, serial port is on chip, timer counter is on chip, and we have seen to make them programmable, we will require a large number of registers. We have seen that those programmable input output ports, we have already discussed 8255, 8253 and details of that, and serial port 828051. There 8251, there we have seen these devices they will require several registers so that the functionality of these devices are programmable. So to do that, these registers of these devices are available as special purpose registers. For example, just I am giving an example, say this is the special function registers of 8051, one of the popular microcontroller. You have seen here, we see that apart from accumulator, B register, this is another register which is used for multiply applications, program status word, stack pointer, data pointer, and these registers P0, P1, P2, P3, these are essentially the register for ports. Then this IP interrupt pointer, interrupt enable, these are also required for interrupt control, and the TMOD, TCON, these are for and TH0, the TMOD and TCON, these are essentially timer control, and these registers TH0, TL0, TH1, TL0, sorry, it will be TL1. These registers are also for timer control. Similarly, these registers are for serial control, SCON and SBUF, and this is for power control. Power control is also very important in microcontrollers because these are battery operated in most of the situations. So later on we shall discuss in detail about the application of these registers, but one point you must notice that here you have, in case of 80851, you have got 21 special purpose registers, and in case of general purpose microprocessors you have got few 5, 6, 8 like that. So the number of special purpose registers available in microcontrollers is very large. Then another important feature of microcontroller is that here we use Harvard architecture. I don't know whether you are aware of the story of the computer design. You know, long back, before the availability of commercial transistors, the US government requested Princeton University and Harvard University to design computers. What for? They were designed to compute tables of naval artillery cell, to compute the tables of naval artillery cell distances for varying elevation and environmental conditions. So essentially to compute the trajectory of a cell, and those distances were, I mean, these universities were asked to design computers so that the table can be created. And at that time Princeton University came out with a design where the program memory and data memory, that means where the instructions are stored and the data is stored, is same. That means that Princeton architecture used common program memory and data memory. So in such a case it looks like this. you have got a single memory address space where you use a part of it as program memory, maybe a part of is stack memory, and a part of it can be used for data memory that can be allocated. So this is the single address space, and you can fetch instructions from here by the CPU. CPU is connected to it, that address bus, data bus, and control bus. And as the as you fetch a particular write from this memory, it is the microprocessor or the CPU which decides whether it is an instruction or a data or the beginning of an instruction. So we have seen that you have to use suitable instructions format so that whether it is data or an instruction is interpreted by the CPU, but it comes from the same memory. And this particular type of architecture was named as von Neumann architecture. Named after the chief scientist of the Princeton University. So von Neumann was the chief scientist, uh, was the who proposed this architecture. And at that point of time, when transistors were not available, the computers were realized by using vacuum tubes. Obviously, the cost of memory was very high. Cost of implementation of memory was very high, and the memory occupied very large space. Memories were not very reliable. At that point of time, this von Neumann architecture was selected and became popular. However, later on in 80s, when the solid state devices became popular, the ICs were available, the situation changed. It was found that the design that was proposed by Harvard University, known as Harvard architecture, where the program memory and data memory are separate. This particular architecture where program memory and data memory are separate were found to be very useful. For example, in case of microcontrollers, we have seen that they are meant for embedded applications, and the application program is ROM based. Obviously, you cannot store data. So it is very convenient if you have separate program memory and data memory. Program memory is ROM based, and data memory obviously will require RAM, read write memory, and that RAM can be separate. And this is one very important advantage. Not only this Harvard architecture is suitable for implementing microcontrollers, they are also very suitable in implementing uh, that pipelining. In case of pipelining, as you know, the instructions are executed, a number of instructions are executed in an overlap manner. That means when you are fetching instruction from memory for one instruction, you are reading data for another instruction. If you have common memory for instruction and data, obviously there will be some kind of problem. It is known as structural hazard. So this structural hazard can be avoided if you have separate program memory and data memory. In other words, it facilitates pipelining and parallel execution of instructions. And that's why in most of the RISC processors, reduced instruction set computers, this Harvard architecture is used. So you will find that in almost all microcontrollers, this Harvard architecture is used, where you have separate program memory and data memory. Program memory is usually ROM or some variations of ROM, as we shall see, and data memory is RAM, and they are addressed through separate buses. So, you have got separate instructions for accessing program and separate instructions for accessing data. So, this is one important feature of microcontrollers. Microcontrollers use Harvard architecture. Now, let us focus our attention to program memory. What are the different types of program memory which can be used in microcontrollers? Program memory is obviously has to be some kind of ROM, but you have got a number of variations. The first one is read-only memory. In case of read-only memory, this this particular device, the ROM is factory programmed. That means at the time of fabrication of the device, this is fabricated, and this memory can be used only when you are producing in bulk. That means you are manufacturing a particular equipment in large numbers, in thousands. Only then it is cost effective, because it is factory programmed. At the time of manufacturing, the fabrication house does the programming of this ROM, and it cannot be reprogrammed. So, this ROM is the microcontrollers are available with ROM as program memory, and this is done only when a particular equipment is already designed, fully tested, and it is going for mass production. So, in that cases you can use ROM based program memory. Second option is to use EPROM. EPROM is electrically programmable ROM. In such cases, as you know, the programming can be done offline with the help of a suitable equipment like EPROM programmer. The programming can be done. However, you have to take out the device from the system and put it in the EPROM programmer, and through and the programming can be done. And you can also do erasing by UV light, and you know that a particular device which uses EPROM has some optical port, and you can expose this device for some duration, so that all the contents of the ROM is erased. That means all of them become one, and then you can do the programming. So, many times this programming can be done. However, there is some limited life cycle or limited number of times you can do programming. You cannot do it for millions of times. You can do it maybe 10,000 or 10,000s of times. So, you can do erasing and programming, but both of them can be done offline, and some microcontrollers are available, you will see with this option, EPROM, and this is good when you are designing a system, developing a system. When you are developing a system, you can use EPROM version. Then as the design and development is over, you can switch to ROM based system by using the same microcontroller. That means a same microcontroller is available with EPROM as the program memory or ROM as the program memory. Of course, there are two more options which can be also used. This one is NVRAM. NV stands for non-volatile. Non-volatile RAM. You may be wondering, you may be asking how ROM can be made non-volatile. What is done? A lithium cell along with control circuit and other functionalities are put on a single chip. All the circuitry, the RAM, the battery, the control circuitry, all are housed on a single chip. Then whenever power goes off, the lithium cell takes over automatically. So the information can be stored for as long as 10 years. So in such cases, since it is a RAM, random access memory, you can do writing, rewriting many times, large number of times. And another type of ROM is also becoming popular, that is known as flash EPROM. Flash EPROM is some enhanced version of electrically erasable and programmable ROM. So it is an extension of electrically erasable and programmable ROM. Of course, in case of electrically erasable and programmable ROM, you can do erasing and writing byte by byte, byte by byte. However, in case of flash EPROM, you cannot do writing byte by byte. Usually all the contents or large blocks are erased in a flash in one go. That is the difference between electrically erasable and programmable ROM. And as we know that electrically erasable and programmable ROM are not very popular because they are costly, unreliable and slow. And that is why the flash EPROM, which has the advantage of electrically erasable and programmable ROM and also the advantage of PROM, EPROM, and so it provides you best of both the worlds, and that is why the flash EPROM has become very popular in recent times. And these are the common program memory devices which are supported by microcontrollers. So this is one important feature. Next is reset circuitry, which needs very immediate attention in case of microcontrollers. The reset circuitry is important because the microcontrollers are used for embedded applications. There is no user. In case of general purpose computers, the user or the programmer is sitting in front of it. If something goes wrong, it can reset the processor, which cannot be done in case of microcontrollers. So you have to use a reset circuitry. Let us see what are the various options. Here is your microcontroller. The simplest one is push button reset, but push button reset can be used only when the operator is readily available. Here is your reset. So of course this is the reset pin. It is assumed that it is low active. So as you can see here, the user can push this button, and then after the power is switched on, the supply voltage is stable, then the user resets this button, and then the processor is initialized and it goes to the execution of the program, usually from the ROM. So this is the simplest. However, there are many situations where users are not available all the time. In such a case, it is necessary to use power on reset. Power on reset can be easily implemented with the help of a resistor and capacitor. You can use a resistor and capacitor combination, R and C. This is connected to reset input of the microcontroller. Of course, in addition to this, we will usually provide a reset switch here. So this goes to VCC, that is usually plus 5 volt. And in this case, how it works? Let us see. Here, as you turn on the power, the supply voltage increases slowly like this. Let us assume this is your plus 5 volt. It reaches this 5 volt level gradually. But the circuitry inside this microcontroller is usually does not function properly until the voltage reaches say 4.5 volt. So what you want? Reset should be withdrawn after the supply voltage reaches 4.5 volt. That means after the supply voltage is stable, then you want the reset is withdrawn. So maybe the reset has to be withdrawn at this point. So mu C reset withdrawn at this point. And this is say 5 volt and this is 4.5 volt, this point. How it is done? This resistor and capacitor, these two are chosen in such a way that as you put the power on, at that point of time the capacitor charge was very small, 0, and as you put the power on, through this resistor it accumulates charge and voltage builds up, and this voltage reaches the high level at this point. Before that point, the voltage here is considered to be low level. That means it remains in the reset condition. So until this point, the input to this reset input is low level, and only after this time, based on this value of R and C, it will be reaching the high level voltage, and then reset will be withdrawn, and by that time the microcontroller has already attained a stable voltage, and the circuits within the microcontroller is functioning properly. But in such a case, the value of R and C has to be chosen in such a way that for such a long duration that reset is held low, reset pin is held low, it has to be high. Now suppose there is a transient or glitch. Because of that transient or glitch, the circuit may start malfunctioning, but this will not be able to reset within such a short time. So in such cases, it is necessary to go for some other circuitry, and that's where comes the power glitch reset. In power glitch reset, usually we use a special hardware. So this is your microcontroller, and we can use a special hardware, say Max 690. Maxim is the name of the company, Maxim 690, and this device is, you are using plus 5 volt as the supply voltage, and this is connected to the reset input, low active, and this is a 8-pin chip, inexpensive, at low cost, and here in this case the the low threshold is 4.65. That means whenever the supply voltage reaches 4.65, only then this line is made high, 4.65, and obviously by this time the microcontroller has already it is already operating properly, all the circuitry within the microcontroller. So this, with the help of this Maxim Max 690 chip, you can do the resetting, and here the low threshold, since the low threshold is 4.65, until the supply voltage attains this voltage, the reset input will not be withdrawn. And in this case, the advantage is that even if there is a glitch on the power line, this will be resetted. So the time constant of the RC circuit does not come into play in this type of power glitch reset circuitry. So you can use an inexpensive hardware to achieve power glitch reset, and this is very important in the context of microcontroller applications where there is no user to take care of this. If there is a glitch, if there is a noise, the system automatically should go to the initial state. But this is not the end of the reset history. The reason for that is, even when the power is stable, there is no glitch, because of some bug in the program or maybe some other problem, the circuitry is not functioning properly. It has gone out of control, maybe some infinite loop or some other thing, it has taken place. The program has gone out of your application program somehow. How do you take care of that? To take care of that, one very important type of reset has been devised, which is known as Watchdog Timer reset. In Watchdog Timer reset, as if there is a watchdog, that watchdog is available in the form of timer. What it does? It keeps on monitoring the processor status. Let me explain the operation with the help of a flow chart, how it works. So this is the normal operations of most of the microcontrollers. After reset, there is some initialization. And after that initialization, usually the application program is performed, but that application program is usually performed continuously in a loop. So before after each execution of this application program, what you do, there is a timer which you reset it, and that timer is known as watchdog timer. Watchdog timer is resetted, and after that it goes to this point. It keeps on looping. So you see, after each iteration of the application program, it resets the watchdog timer, then goes back to the application program. Then this resetting is acting as a resettable monostable multivibrator. But suppose if it does not execute the application program, then resetting will not take place. If it is not executing the application program, it will not come to this point and resetting will not take place. Then what will happen? Then the watchdog timer will reach the terminal count, and as it reaches the terminal count, it jumps to watchdog timer service routine, and the function of the job of the watchdog timer service routine is to initialize the processor, bring the processor back to the well-defined initial state. So I can show it in this manner. This is the watchdog timer timeout. As it times out, then it goes to watchdog timer interrupt service subroutine. What is the outcome of this? The outcome of this is that it goes to this point. So again, the system is initialized and it is brought back to the initial condition. It is a common experience of any computer user, and on many occasions you have to press the reset button while executing programs. But here in case of embedded applications there is no user. So it is done with the help of a watchdog timers, and the watchdog timer automatically brings the microcontroller back to the well defined initial state. Then it again goes on doing its executing its application program. For example, in ATM machines, you insert your card and provide your numbers and everything. So there also you will require a watchdog timer. Suppose at some point of time, if the key is not depressed for maybe 2 seconds, then watchdog timer will become active and it will go to the initial state, it will, and your card will come out from the machine. So this is a simple use of watchdog timer. So this type of applications, in this type of applications you require watchdog timer. And I believe there is another important feature which is essential in microcontrollers, that is interrupt structure. You require a very powerful interrupt structure in case of microcontrollers. Why? Embedded applications are many, a large number of embedded applications are used for real-time applications. And in real-time applications, it is not only important to carry out a job, but it is also very, very important to carry out the job within some well-defined time. If a task is not performed within some well-defined time, it may lead to catastrophic situation. Suppose you are doing missile control. If the missile is not fired at proper time, the target cannot be hit. Or you are trying to use it for protection, then protection will fail if some actions are not done at proper time. So time is very important in real-time applications. And how this time is taken into action, and obviously this time has to be done with interaction with the outside world. How the interaction with the outside world comes? It is through interrupts. Outside world is interacting with your microcontroller through the interrupts. So it is very important to have a very powerful interrupt structure. But you may be asking, what do you mean by a powerful interrupt structure? There are several issues. Number one is you must be able to the interrupts you should be able to masking feature. So whenever you want that a particular interrupt is activated, the other interrupt should be masked. So the interrupt should be maskable. Second is you must have the facility of enabling interrupt. Disabling interrupt. You must have the facility of enabling and disabling interrupt. Moreover, the switching from one interrupt of which is known as context switching. Switching from one interrupt to another interrupt or interrupt response should also be very fast. We have seen that whenever you have got a large number of interrupts, first job that has to be done is to identify the source of interrupt. If you do it by software, it takes very long time, that we have already seen. If you do it by software polling, so you have to use some you cannot use software polling technique in case of microcontrollers. So commonly you use vectored interrupt. So the interrupts are provided with fixed addresses, and whenever an interrupt occurs, automatically the source of interrupt is detected and it jumps to that interrupt service subroutine. And also it is important to provide priority. There will be some interrupts which are important, some interrupts may not be that important. So these are the features which are necessary to provide in the interrupt system, and by that I mean powerful interrupt structure. Later on we shall consider some specific application, specific processor, and see how this powerful interrupt structure is provided. So these are the vital features of microcontrollers. I have not discussed any specific microcontroller so far because there exist numerous microcontrollers. Say these are the 4-bit microcontrollers. It started with 4-bit microcontrollers, Hitachi HMS 40, available in 428 pin. You can see the input output lines are provided, 32 bytes of RAM, 512 bytes of ROM, and it is addressed by 10-bit ROM, and these are the features. And you have got 8-bit microprocessor, large numbers, Intel 8048, Intel 8051, Microchip, National, Motorola, Rockwell, Philips, Texas Instruments, Zilog, many manufacturers with variety of number of pins varying from 28 to 68. And each of them provides a large number of input-output lines, varying sizes of RAM, on-chip RAM, starting from 64 bytes to maybe 256 bytes, varying sizes of ROM, 1 kilobytes to 8 kilobytes, variable number of timer counters, 1 to 3, and they have some typical features. Microcontrollers are also available in 16-bit and 32-bit. These are the 16-bit microcontrollers with 84 pin or 68 pin, having RAM of 1K, ROM of 32K, and this is the ultimate powerful microcontroller, Intel 80960, very powerful, very sophisticated microcontroller, and it is available in 132 pin, operates at 20 megahertz, so you can see it is very fast. 32-bit bus, it is provided with floating point unit, 500 by 12 bytes of instruction cache, and it is intended for very sophisticated applications like robotics, avionics, image processing, telecommunications, automobiles, etc. However, we cannot discuss everything in this class. So we shall concentrate on the most popular 8-bit microcontroller, and you will see this 8-bit microcontroller Intel 8051. This one is the most widely used, very popular microcontroller. We shall discuss in detail about this microcontroller, how you can design systems around this microcontroller. All these things we shall discuss in the subsequent lectures. Thank you.